Good day, ma'am. I'm Joseph D. Machado Jr. from BCE 1B, Lecture 4. That's from the topic Conversation of Energy, Momentum, Impulse, and Collisions. Problem set number 1. CYU, page 374. Check your understanding. How high above the bottom of its arc is the particle in the simple pendulum above, when its speed is 0.81 meter per second? Given. Velocity is equals to 0.81 meter per second and length is equals to 1 meter. So, mo ni siya. The longest hypotenuse, 1 meter. And beta is equals to 30 degrees angle. And gravity is equals to 9.8 meter per second square. So, ang atong gipangita is H is solution. We are neglecting non-conservative force, so we write the energy conservation formula relating the particle at the highest point, initial, and the lowest point in the swing, as K initial plus U initial is equals to K final plus U final. Since the particle is released from rest, the initial kinetic energy is zero. At the lowest point, we define the gravitational potential energy to be zero. Therefore, our conservation energy formula reduces to 0 plus mgh is equals to 1 half mv squared plus 0. mgh is equals to 1 half mv squared. Supposed to be, we will be bring down mg, then copy the sign the over mg, so we cancel out the same mg, then this one m cancel out, so ang mabilin is 1 half v squared over g, then h. So ato din i-substitute ang 1 half is equivalent to 2h is equals to v squared over g, or velocity squared over gravity. So our velocity is the quantity 0.81 meter per second square over gravity is which is 9.8 meter per second square. So ato ding i-multiply kaduhon 81 meter per second square. So ang answer is 0.6561 m square per second square over, then ato gyapon ni kaduhon 98 meter per second square. So ang iyang is 9.8 meter per second square. Then atong eliminate ang m same square square square. So ang mabilin is m. Then we are going to compute this 0.6561 over 9 over 0.8. So the answer is 0.0669 m over 2. So 2h over 2, copy, then cancel out 2, so ang mabilin is h. So the answer is 0.033 m. Insakto siya sa answer key dito sa libro. Number 3, example 9.1, page 400 to 403. The Arizona meteor crater, approximately 50,000 years ago, a large radius of 25 iron-nickel meteor collided with Earth at an estimated speed of 1.28 times 10 raised to the power of 4 meter per second in what is now the northern Arizona desert in the United States. The impact produced a crater that is visible today. Figure 9.7, it is approximately 1,200 meter, 3/4 of a mile in diameter, 170 meter deep, and has a rim that rises 45 m above the surrounding desert plain. Iron-nickel meteorites typically have a density of P is equals to 7,970 kg per meter cube. Use impulse and considerations to estimate the average force and the maximum force that the meteor applied to the Earth during the impact. Solution: define upward to be the positive y direction. For simplicity, assume meteor traveling vertical downward prior to impact. In that case, its initial velocity is v initial is equals to negative v initial joule, and the force Earth exerts on the meteor points upward. Force, the quantity T is equals to positive force, the quantity T joule. The situation at T is equals to 0 is depicted below. Given V initial is equals to 1.28 times 10 raised to the power 4 meter per second. Radius is equals to 25 m, then 7,970 kg per m cube is density. Solution: the average force during the impacts is related to the impulse by average force is equals to J over delta T. From equation 9.6, joule is equals to m delta V. So we have the average force is equals to m delta V over delta T. The mass is equals to the product of the meteor's density and its volume. M is equals to PV. If we assume that the meteor was roughly spherical, we have velocity is equals to 4 over 3 pi r squared, and joules is equals to m delta V. So we're going to substitute P V delta V over delta T is equals to P 4 over 3 is our velocity over 3 pi r squared. Then V final minus V initial over delta T is equals to 7,970 kg over m squared. 4 pi over 3 times 25 m cubed, then 0 meter per second minus negative 1.28 times 10 raised to the power of 4 meter per second joules over 2 seconds. So we are going to substitute this one. The quantity 7,970 kilogram over m cubed. Then 65,286.2 m cubed. The quantity 1.28 times 10 raised to the power 4 meter per second joules over 2 seconds. So, our final answer is average force is equals to the quantity 3.33 times 10 raised to the power of 12 Newton joules. The problem says the velocity at impact negative 1.28 times 10 raised to the power 4 meter per second joules. The final velocity is 0. Also, we guess the same direction as the change of velocity vector delta v. Next, we calculate the maximum force. The impulse is related to the force function by joule over integral T initial T max F, the quantity T or time dt. We need to make a reasonable choice for the force as function of time. We define T is equals to 0 to be the moment the meteor first touches the ground. Then we assume the force is a maximum at impact and rapidly drops to 0. A function that does this is force, the quantity T is equals to max force E negative T square over the quantity 2 pi square. The parameter R represents how rapidly the force decreases to 0. The average force is equals to 1 over delta T integral 0 max T. Max force E negative T square over the quantity 2 pi square dt, where delta T is equals to T max minus 0 seconds. Since we already have a numeric value for average force, we can use the result of the integral to obtain F max, choosing R is equals to 1e T max. This is a common choice, as we will see in later chapters, and guessing that T max is equals to 2 seconds. This integral evaluates to average force is equals to 0.458 force max. So we're going to substitute 0.458 F max over 0.458. So copy 0.458 is equals to 3.33 times 10 raised to the power of 12 Newton over 0.458 is equals to 7,227 times 10 raised to the power of 12 Newton. Then cancel out, ang mabilin is F max. So mao na siya atong answer. The last number for example 9.3 page 406. Mr. Sulu, take us out ahead 1/4 impulse with this command, Captain Kirk of the Starship Enterprise. In figure 9.11 has his ship that start from rest to a final speed of V final is equals to 1/4 the quantity 3.0 times 10 raised to the power meter per second. Assuming this maneuver is completed in 60 seconds, what average force did the impulse engines applied to the ship. So, given which is V final is equals to 1/4 the quantity 3.0 times 10 raised to the power of 8 meter per second. V initial is equals to 0 meter per second. Time is equals to 60 seconds. So, our mass of the Enterprise is equals to 2 times 10 raised to the power of 9 kilogram. So, ang atong gipangita is F or force. Solution. Because this problem involves one direction, the direction of the force applied by engines, we only need the scalar form of the impulse momentum theorem, equation 9.7, which is delta P is equals to Joule, with delta P is equals to M delta V, and Joule is equals to F delta T. So we're going to equating these expressions gives F delta T over delta T is equals to M delta V over delta T. So we're going to cross out the same delta T. So ang mabilin is F, or which is force, is equals to M delta V over delta T. So our mass of the Enterprise is we're going to solving the magnitude of force and inserting the given values leads to 2 times 10 raised to the power of 9 kilogram multiplied by 7.5 times 10 cube meter per second over 60 seconds. So the answer is 1.5 times 10 raised to the power of 17 over 60 seconds. So we're going to compute this one. So the answer is force is equals to 0.5 times 10 raised to the power of 15 Newton. In this unimaginably huge force, it goes almost without saying that such a force would kill everyone on board instantly, as well destroying every piece of equipment. Fortunately, the Enterprise has inertial dampeners. It is left as an exercise for the readers' imaginations to determine how this works. That will be all. Thank you.